Here is our little red wagon being pulled on by two forces. And earlier we looked at how to find the resultant of those two forces by drawing a parallelogram. And we hinted that maybe it would be faster just to use half that parallelogram, a triangle, and we'd come up with the same result. And right you are. Here was our motorboat, and last time we tried drawing a picture of those two forces and drawing a parallelogram around them, and that let us find the resultant, the one force that would have the same net result as those two individual forces. But what if we just draw half of that? What if we just draw one triangle and use that to find the resultant? It would look like this. And what you do is you take one force and you put its tail next to the tip of the other one. That's what I did here. And look, there's the same resultant, same length, same angle. It turns out it doesn't matter what order you do that. Here's our bolt that we've seen before with a 500-pound force pulling straight up and a 1,200-pound force pulling to the side. And if you wanted to do that tip-to-tail method, you could take the tail of the long one and stick it onto the tip of the short one, and there's the resultant. Or you could take the tail of the short one and stick it onto the tip of the long one, and there's the same resultant. You get the same result no matter what order you stick them together, so that's good. Here are two forces pulling, one's horizontal, one's at an angle, and let's find the resultant of those two forces. In other words, what is the one force that would have the same net result as those two smaller forces? Well, we could leave the shorter one where it is and move the longer one, move its tail onto this tip. There's the resultant. Or we could leave the longer one where it is and move the shorter one with its tail on that tip. And there's the resultant. So you can see, you can do them in either order. You'll get the same resultant, the same net result. And what you do when you stick them tip to tail, to find the resultant, you start at the start of that string of arrows. You start at the start, you head off towards the end, and there's your resultant, and there's your arrow pointing towards the end. Or if you arrange them in a different order, start at the start, head off towards the end. There's the arrow pointing towards the end. This is how you can know which direction your arrow should point in. That is, what sense. So with the tip-to-tail method, you string them together, tip to tail. You start at the start, you head to the end, there's the resultant. Tip-to-tail method. Tip, tail, strung together. Start at the start, head off toward the end, there's the resultant. Here is a practice exercise we're going to look at in CAD if you want to. This one is very similar to our next homework problem, that the first finding a resultant that you're going to draw in CAD. So in a minute we'll go look at how you would do that in CAD. This is the practice problem, and it's very similar to your homework problem, which looks like this. So in your actual assignment, there's a 100-pound force at a 40-degree angle. There's a 200-pound force at a 20-degree angle, and you're going to find the resultant of those two. You can use parallelogram or tip-to-tail. I recommend tip-to-tail because I just think it's faster. And then you're going to label them, how big is the magnitude, and you're going to give a dimension showing the angle of the resultant, and you'll have an arrowhead showing what sense it has. And here at the bottom of the slide is the answer you should come up with. It should be around 173 pounds of magnitude at a 50-degree angle above the 0 line. And as you might notice, the arrow should point sort of up and to the right. Then here's the second problem in your assignment. Again, two forces pulling outward, and you could use either the parallelogram or the tip to tail to stick them together. Remember to label the magnitude and the angle and have an arrowhead showing the sense. And the answer you should come up with is around 716 pounds, and it should be an angle of about 72.5 degrees above the 0 line. Now, in engineering work, especially the first rough cut of a problem, we're always kind of approximate. And your numbers might be a little bit bigger or a little bit smaller. That is fine. As long as you're in the ballpark, that'll be good. So I'll stop here, and now we'll go look at a CAD drawing.